And away we go. Here we go with Unit 3. This is going to be turning into differentiability, finding derivatives and things like that. All right, so here we go. The beginning of this is finding a derivative using the limit process. All right, so let me open up a new screen here and kind of describe what is this quote-unquote limit process. All right, so the definition of a derivative is the slope of a tangent line. All right, it's an instantaneous rate of change. Okay, it's a slope of a tangent. And when you talk about the limit process, there's a couple different ways of going about it. Okay, if you just want to know what a derivative is, just in general, like not at a specific point or anything, this is the equation that you want to be using. The limit as h goes to 0 of f of x plus h minus f of x all over h. All right, and so what that will do is this. Let's say I have this f of x. What that will hypothetically do is it will give you the slope of a tangent line. Okay, it'll give you a slope of a tangent line at any point that you so desire on this. It will give you an equation. All right, it'll give you an equation, and the slope of the tangent line at any x that you so desire, you can get using this limit equation. Now, sometimes in mathematics, you don't want an equation. You don't want an infinite number of tangent points. What if you want a very specific slope at a very specific point? Like, I want to know this when x is equal to -1 or something like that. What is the slope at that one very specific point? All right, and we can use a couple different equations. The limit as it's a goes. Here's the most basic one. As x goes to a, it'll be f of x minus f of a all over x minus a. Okay, that is another basic equation, or another version of just the top guy up there would be h goes, excuse me, as you were. Let's call it a again. A goes to 0 of f of x plus a minus f of x all over a at a very specific point. I think that might be wrong, actually. Check that. I'll get back to you on that one. Check that. I know these top two are absolutely correct. And what the a is the x coordinate that you want. The like it'd be like the -1 in my previous example. Okay, but this is the dude that we're going to be using over and over and over again. Okay, this is the dude that we're going to be using over and over and over again. And so that's what our beginning problems are technically asking for. So find the derivative using the limit process. So in number 13, we want the limit as h goes to 0 of f of x plus h minus f of x all over h. So what that means is this is going to be the limit as h goes to 0. Okay, f of x plus h. That'd be -5 x plus h. So all I'm doing is I'm using the f of x, and I'm replacing the x with x plus h. Minus f of x. So that'd be minus -5x all over h. That'll drop down to this next line. I'll distribute into that first parentheses. So this is negative 5x minus 5h. And then it is plus 5x, because the minus of the negative, all over h. Excuse me, all over h. Notice that negative 5x and adds 5x. This is going to happen a lot. So this leaves us with negative 5. Sorry, rules of limits. The limit as h goes to 0. Notice that the h drops and there's no more illegal mathematics. So this is equal to negative 5. All right, number 18, the limit as h goes to 0 of f of x plus h minus f of x all over h. So f of x plus h is going to be x plus h squared minus 5. Okay, so that is the f of x plus h minus f of x, which is x squared minus 5, okay, all over h. Okay, in this very first green, the f of x plus h portion, this is going to be x squared plus 2xh plus h squared minus 5. And then here, this negative has to distribute. And so that's going to be negative x squared plus 5 all over h. All right, simplifications. I see that I have a minus 5 and a plus 5, a negative x squared and a positive x squared. Okay, so what this second piece will do, this is like a cancellation piece. It will cancel everything in there all the time, leaving everything with h's. So here we go. H takes out one of these h's and one of these h's. So I'm left with, as h goes to 0, of 2x plus h. So if h goes to 0, this is equal to 2x. That'd be 2x plus 0. The limit as h goes to 0 of f of x plus h minus f of x all over h. So this is the limit as h goes to 0 of square root of x plus h plus 4 minus f of x all over h. Okay, what I'm going to do is I'm going to multiply this top side by the conjugate. So I might have to make my work a little bit smaller here. Limit as h goes to 0. And so this is x plus h plus 4 minus x plus 4. And so what I'm going to multiply this numerator with is x plus h plus 4 plus x plus 4 technical break right there. h, and then so whatever I multiply the top, I have to multiply the bottom. But this should get us going in the right direction, I think. I hope. All right, so as I said, I probably have to minimize this a little bit just so I can fit it on the screen here. Writing with this this board marker is like writing with a crayon or something like that. It's not very efficient. All right, so I'll kind of keep minimizing as I go along here. All right, the reason that I multiplied by the conjugate, what this will yield is, you know, think of something simplistic, x minus 4 multiplied by its conjugate, x plus 4. What you're going to end up with is x squared minus 16. So what you're doing is you're, in essence, squaring both of those terms by multiplying by the conjugate. And that, in this case, so if they're square roots, they will come out to be not square rooted numbers. All right, so this will leave us with x plus h plus 4 minus x plus 4. That's where it'll leave us. So you square, it gets rid of the square root in essence. So now you create a square root on this bottom, but I don't really, what my mission in this universe right now is to somehow get rid of that h, that very specific h right there. That's really, really, really what I'm after, because I can't divide by a 0 if I take this limit. So I have to use everything in my power to get rid of that, that h. All right. So multiplying in this negative, what I will be able to do is I am able to cancel out this negative x with that x, this negative 4 with that positive 4, leaving just an h in the numerator, and there is my cancellation with that h in the denominator. So I was able to cancel out that h that I was really looking to get rid of. So what I have left is the limit as h goes to 0 of nothing on top, so that's a 1. And I have x plus h plus 4 plus x plus 4. And so now I'm able to turn this h into a 0. So this h into a 0 is a 0, and this final result will be x plus 4 plus x plus 4. So this is, oops, sorry, getting ahead of myself. This is a 1. Sorry, this is a 1. And so this is going to be 2x plus 4 underneath 1. Okay, use a graphing utility to graph the function and find the x values at which f is differentiable. All right, so what this section is dealing with, let me go to a new screen, is to be differentiable, that in essence means it's smooth. It's smooth, right? So it's differentiable all along this smooth path right here. If it's smooth, it's good. If it's herky-jerky, it's not. So things that are not, quote-unquote, differentiable Corners. This is a corner. It's differentiable all along this line and all along this line, but it is not differentiable at the point. So corners. This thing is called a cusp. A cusp. It's not differentiable at a cusp. Any discontinuities, it's not differentiable. It's not differentiable at discontinuities. And it's also not differentiable. I didn't really do a good job here. Let me try that one more time. It's not differentiable at places that would technically have a vertical tangent. Okay, it's not differentiable at a vertical tangent. Okay. Those are discontinuities. Those are discontinuity, or excuse me, non-differentiable places, non-differentiability. So corners, cusps, discontinuities, and vertical tangents. Those are the big no-nos where they're not differentiable. Okay, so this is asking, where is it differentiable? So drawing a quick mental picture of this, this is going to be right 1. So it's differentiable everywhere except for this corner. So where is it differentiable? Well, it's differentiable for all real numbers except x is not equal to 1. It's not differentiable at positive 1. All right, next we have x to the 2/5. I'm just going to graph it here real quick. All right, so it doesn't show it superbly right here, but what this is doing is this. It's spiking down. It's like a square root, kind of like that way, a 5th root, but a square root, and then like another root coming off of this. So this is a cusp. This is a cusp right at the center. So where is it differentiable? It's differentiable for all real numbers, except x is not equal to 0. It's not differentiable at 0 because of that cusp. Okay, the graph of a piecewise function g is shown. The graph has a vertical tangent line at x is equal to -3. So this is a vertical tangent right where I kind of made this little red dot. So what are the values of x on interval from -4 to 4 at which g is continuous but not differentiable? So continuous. Continuous just implies that you don't pick up your pen or pencil. That's what it means to be continuous. So for instance, that is continuous. I never picked up the marker to create that. So it's continuous, however, it's not differentiable right at that point. So continuity implies that you don't pick up your pen or pencil, there's no holes and things like that. And then differentiability just implies that it's smooth. It's smooth, no sharp corners. Okay, so looking for non-differentiability would be this vertical tangent right there. It is continuous, but not differentiable. So -3 is where it's continuous, but not differentiable. At 0, it's not it's not continuous. So 0 is not continuous. So we're looking for continuous, but not differentiable. Another important point, 2. 2 is continuous, but it's not differentiable. So the answers that I have that they're continuous but not differentiable are -3 and 2. Which corresponds to the graph of f prime. Okay, so this little like what is it, apostrophe is called a prime, and this is it's a derivative. So like the things that we were doing at the very beginning. So if I said f of x is equal to -5x, f prime of x is equal to -5. It's derivative. In number 13, excuse me, in number 18, if f of x is equal to x squared minus 5, f prime of x, its derivative, is equal to 2x. Its derivative. All right. So that's what that symbol means, that little thing. And it's called prime. So this is f prime. Okay. If there's two slashes, it'd be double prime. That sort of thing. It's a derivative. It is the derivative. It is the slope of the tangent. All right. Number 90. Which function corresponds to f prime? Okay. So if f prime is that, that is the slope of the function or whatever. That's the slope. Okay? So for instance, what is the slope of this unshown graph at x is equal to 2? Well, it's 0. Okay? What is it to the right of the 2? Oh, it's positive. What is it to the left of the 2? Oh, it's negative. So what this is something that will look maybe something potentially like this. Maybe potentially something like this. Okay, maybe potentially something like this, where you notice what is the slope at this 2? Oh, it's 0. The slope of the tangent is 0. What do I notice about the slope to the right of that 2? Oh, it's positive. But notice that the positivity gets more and more and more positive. So that means the slope of this thing has to get steeper and steeper as you go along. Same to the left. It's small, but then it gets more steep because the line gets more and more negative. So a potential result of this is, okay, this has a slope of 0. It's positive on this side, getting more positive, and the slope is negative on this side, okay, getting more negative as you get away from the 2. All right. So this is kind of what we're looking for. So what I notice is B is instantaneously not a correct answer. And I need a vertex of this to be at 2. And again, how you can kind of tell where a vertex is -b over 2a. That will give you the x-coordinate of the vertex. So -b over 2a, -b over 2a, -b over 2a. What has a vertex at 2? It's this letter D. This kind of flirts with some of the like more advanced calculus that we'll talk about, obviously, a little bit more down the road. What I really kind of know is this. If a derivative is 0, usually that's a max or a min of something. Usually, not all the time, but usually it's a max or a min of something. Also, I noticed that the derivative is a line. Derivatives are often whatever the largest exponent reduced by 1. All right, so if I noticed that this is a line, aka an x1, that means it probably originally came from an x squared of some sort. So if I see a derivative that is a parabola, so if I see a derivative that is a parabola, chances are, what did that come from? That came from something that is an x to the third. Again, this is kind of flirting with a little bit more advanced stuff than what we're ready for right now. But this has a slope of 0. It's positive to the right of it. It's negative to the left of it. And so parabola fits the thing. Okay, that's it. So a derivative is a slope of the tangent. A derivative is the slope of a tangent. And this is that big using the limit method. Okay, this is the equation that you want right now. This will get you the derivative right here, this equation up here. All right. Again, if you're lost or you need to see this broken down or explained a little bit better, please bring up your questions in class. Have a good day.